In this video, we're going to look closer at the topic of force fields and specifically take some time to look at something called field strength and how we can draw force fields. And we're going to be looking at, in this video, electrostatic and gravitational force fields and how we're going to depict and calculate for those. So to start us off, let's do a quick warm up and just remind ourselves how we use some of this gravitational or any sort of force field force calculation. You might recognize this formula as Newton's universal law of gravitation. It's big G, this universal gravitation constant, times the mass of one object and the mass of the other, divided by the distance between them squared. Well, all of those factors are given to you here for the Earth mass, the Moon's mass, and the distance between their centers. Now, something that gets really annoying is all these numbers are super big, so we're going to have lots of scientific notation acting up here. The most common thing that is easy to miss here is calculating that distance between them and remembering to make sure that that is squared. Just because it's such a big number that you've already typed in, to remember to square that is really important because if you don't, you're going to be very, very wrong in your final answer. Well, here we can find that the force of gravity that's acting is 2.05 times 10 to the 20 newtons. A really, really large force that's allowing that moon to orbit and create that circular motion. We could look deeper into this and actually figure out that this is the centripetal force that's acting. And since we know the centripetal force, we know the radius, we can calculate from this mass what the velocity is, either its angular velocity or its linear velocity, to find that for the moon. Well, we're not going to do that right now. Instead, let's look at this idea of force fields. Vector field that describes the force and how the force would act on a particle at various positions. So basically, what we can kind of think of it is it's a map. It's a map around either something that has a static charge or something that has mass. And the map tells us if something were placed here, here's what it would experience. Here's the force that it would experience. Well, if we're talking about field strength, we have a couple different ways that we can represent that. And let's look at both of these together because they parallel each other really nicely. Electric field, we are going to use a field strength symbol of a capital E. And a gravitational field, we're going to use a lowercase g. We'll call that little g. Now, the unit for an electric field is newtons per coulomb. It can also be written as NC to the minus 1. For a gravitational field, we're going to talk about that as newtons per kilogram. Notice here it's a very similar format. It's taking the force and dividing it by however we're quantifying that thing. For electric field, we're quantifying it by its charge, and a gravitational field, we quantify it by its mass. So when we're drawing it, there's a couple of notations that you need to know of. Electric fields are always going to point in the direction that a positive charge would travel. Sometimes we call this a test charge. So imagine that you have this object that's positively charged right there, and we place another little positive charge somewhere around that original object. Well, the field is going to point at whatever direction this positive charge would travel. Well, these two like charges are going to repel, so this positive charge is going to be pushed away. Likewise, if I put a positive charge down here, it's going to be pushed away in this direction. And I could do that in every possible location. Notice here, the closer it was, the longer that force arrow, that force vector is drawn, because it's going to experience more force with less distance. Well, anywhere that I place this, I'm going to find that that positive test charge is pushed away. So my electric field is going to be pushed outward in these directions. Now, a negative test charge or a negatively charged object is still going to be tracked for our electric field using this positive test charge. So imagine I put a positive charge right here. Well, these are opposite charges, so we're going to attract. And a positive charge over here is going to experience attraction as well. And no matter where I draw that, I'm always going to see that force pointing inward. So electric fields around a positively charged object will point outward, and around a negatively charged object will point inward. So if I were to give you a diagram that looks like this, but I hid whether it's positive or negative, that's still enough for you to determine which one's positive and which one's negative. As we said earlier, the positive charge points outward and negative charge points inward. Or you can imagine I place a positive test charge right here. Well, it's being repelled away from whatever this is. That must be a positive. If I place a positive here, well, it's being attracted to whatever this is. That must be a negative. So we see this sort of arcing pattern that shows up. We'll get deeper into this idea, especially when we get into magnetic fields, of why it's making these big arcing loops. But for now, recognize if the arrows are going out, that must be a positive charge that they're moving away from. All right, we can also make some predictions here. What if we had two of the exact same thing? What if we had two positive charges? Well, I can factor in a couple different locations. If I put a positive charge here, I expect it's going to just move outward. Positive charge here, I'd expect it to move outward. Positive charge up here, well, both of these are pushing it away, so it would probably move just up. Um, so that's going to result in some interesting looking vectors. We get a pattern that looks something like this. It's possible you could find a space right in the middle here that everything cancels out and you don't have any field at all. But most of the time, you'll end up somewhere offset that is eventually going to be pushed outward, and we'll see these arcing patterns showing up like this, showing repulsion from both of these test cases. All right, if we have gravity as a field, it's a little bit simpler because gravity can't repel. Gravity has one direction, gravity can only attract. So our field is going to look something like this. Um, Pretty easy. It's never going to be pointing outward, always going to be pointing in towards that object with mass. It can get more complicated though as we start to add more things. So space has a lot of different bodies with mass. The Earth isn't the only one, the sun isn't the only one. There are all sorts of different massive objects around space. And one way to think of gravity field is thinking of it as a distortion of space-time. So imagine here we have this sheet that if there was no massive object would be perfectly flat. But any massive object like the Earth distorts that sheet. So it bends it inward, distorting space-time and creates kind of this inward pull towards itself. If I were to place, like imagine here, I place a marble right here, well, it's going to experience an inward force towards the earth like this, based on the slope of that sheet. If I place it farther out, it's going to still experience a force inward towards the earth, but it's going to be less. The slope is a little bit less there. So gravity as a field can be thought of as massive objects distorting space-time. This is a way that we can visualize it as two dimensions. You might be thinking, well, it isn't two-dimensional, it's three-dimensional. How do I picture that? Well, it's a lot harder to draw, I can tell you that. It's a lot harder to visualize as well. So this two-dimensional visual is enough for us for now to be able to picture and understand what gravity is doing here. Where this can become really useful is imagining these multiple massive bodies all distorting space-time a little bit differently. And this gravitational field distorts, and it allows the field to kind of factor in these different masses that are around. So bigger masses will curve the sheet more than the smaller masses. And there are spots here that are kind of these equilibrium spots that you could find a spot that was like right in the middle, not necessarily equidistant to each of them, but in a spot that it isn't attracted to one over the other. Here, if I put something right in the middle of this zero point 0.1 kilogram and this 10 kilogram, well, the larger field is the 10 kilograms, so it's going to experience a force towards there. It's not balanced out. We'll see that a little bit more with numbers in just a minute. Now, we're not usually going to draw it as this distorted sheet. That's just really hard for us to draw. So instead, we'll typically be drawing these fields as just a field of vectors. There are two different ways that we can visually show how the strength of the field is changing. One way is by looking at the vector's length. Notice here, the farther away, the smaller the vector. The closer you are, the larger the vector. As we know, the closer two objects are, the stronger the field, the stronger the force is going to be between them. That is universal law of gravitation. That's that r squared factor. Another way that we can represent that field getting stronger as it gets closer is we can draw just individual vectors that are converging on this space. And another way that we can look at it is vector density. So here, closest to the planet, we have the highest density of vectors, which is another way of showing without individual arrows, showing that the vector field strength is largest towards that massive body. All right, there are some formulas here in the IB Physics data booklet that'll be helpful. In subtopic 5.1, you'll see this formula, E is equal to F over Q. In subtopic 6.2, you'll see a couple different formulas for this G, gravitational field strength. The first, F over M, parallels really nicely this other value here. So E is F over Q, G is F over M. It's taking the force divided by however we're quantifying that object, either a charge or a mass. And then here's another way that we can calculate gravitational field strength using the mass of the object that you're surrounding, this gravitational constant, big G, and the distance you are from that object. We're going to look at both of those derivations here in just a minute. All right, you might remember back to when we talked about kinematics and free fall. We used this number 9.81. That should be a familiar number to you. We talked about this as acceleration. That's how fast gravity accelerates an object as long as there's no air resistance. Well, this was a simplification. This is true if you are pretty much at sea level, at the surface of our planet. But that is not true everywhere, and it's not true for any necessarily gravitational field. It's specifically Earth's gravitational field at the surface. We have another way that we can talk about G, not necessarily as acceleration. We call this more generically the gravitational field strength. And gravitational field strength that we talked about a couple slides ago was newtons per kilogram. Well, how can something be newtons per kilogram and meters per second squared at the same time? Well, if you open up this unit and look at its fundamentals, you're going to notice that it's exactly the same unit. So if I expand newtons into its fundamental units, kilograms times meters per second squared, if you're not sure where that comes from, F equals ma, force is mass times acceleration. Here's our mass, here's our acceleration. Well, if I present it like this, I can see pretty clearly that the kilograms are going to cancel, and it leaves me with just meters per second squared. So newtons per kilogram simplifies out to meters per second squared if you want it to. These are the same thing. We just used that as an acceleration before. So why might this be more useful? Well, there are a couple different things that we can do here. It means that G changes. So on the surface of the Earth, G was 9.81. But the farther you get from Earth, the smaller G is going to be. Here, the International Space Station is 400 kilometers above the planet. This is definitely not to scale. 400 kilometers actually looks way, way closer to the Earth. I'm just using this to make it a little easier to see. Here is one of the formulas that we had for little g. It's big G times the mass times or divided by the radius squared. Well, our total, well, I said radius, that's the distance to the center, basically. Our total distance, the distance all the way to the center, is 600 or 6,770 kilometers. If I take that and the mass of the Earth, which isn't shown here, but the mass of the Earth, that distance converted into meters, and this gravitational constant, I get a value that's showing here as 8.73 newtons per kilogram. I'm realizing now that this is misinterpreted. That should be a lowercase g, not a capital F. So lowercase g is equal to 8.73 newtons per kilogram. That is a little bit less, not a lot less, but a little bit less than gravity was on the surface of the Earth. That gravitational field strength has diminished the farther up we get. It isn't totally gone, when we talk about astronauts being weightless, we're talking about something totally different. They're falling at the same amount as the orbiting altitude in this space station that's orbiting the Earth. But there is still gravity. That gravitational field strength is just a little bit less than it is here on the surface. So we can use that. One of the great parts about using this definition of it as newtons per kilogram is this a really clean way to think about how you can find the force of gravity for these positions. We talked about force of gravity before, basically using the same thing. We said force of gravity is mass times gravity, and gravity was always 9.8. Well, here, gravity can change, or this g value, little g can change. Say we have little g being 5 newtons per kilogram. Well, if I take that as my unit, it's really easy to see that just taking your mass, in this case the astronaut, the mass of 75 kilograms, times 5 newtons per kilogram, the kilograms cancels, and you're left with just newtons. So that turns into 375 newtons. I can do the same thing with the space shuttle, just plugging in its mass, and it will give me a force in newtons as well. Now, if I do the same thing at a slightly lower elevation, closer to the planet, we'll see that the force is larger for both the astronaut and the space shuttle. So the farther away you are, the smaller that gravitational field strength. But all you need to do is just multiply that field strength by the mass, and that's enough to figure out what the actual force is, because the force depends on the mass. So this is a nice shortcut to allow us to get there. So we can do the same thing with electric field strength. Just because we've been focusing on gravity doesn't mean it's that different. Electric field strength is just the force divided by the charge. Well, if I know that the force that's experienced is 0.0025 newtons and the charge is 6.3 microcoulombs, I can convert that to coulombs and plug it in. Well, to convert that to coulombs, it's 6.3 times 10 to the negative sixth. Put that as Q, the charge, and the force is 0.0025 newtons. That gives me an overall electric field strength of 307 or 397 newtons per coulomb. If you're not sure what the units are, just look at what you're doing in this equation. Newtons divided by coulombs, it'll get you there. All right, one of the trickiest and one of my favorite types of questions that you'll see on the IB exam are questions like this. Two isolated point charges here, a negative 7 microcoulombs and a positive 2 microcoulombs are a fixed distance apart. We're not given that. We just see them here, position B and D, or B and C. At which point is it possible for the electric field strength to be equal to 0? So what we're thinking about here, just to give you a sense, is if we were to place a positive charge somewhere, there is a point that we could expect that positive charge wouldn't move at all because it's being attracted to one of these charged particles exactly the same amount as it's being repelled by the other. So an easy way that I can visualize this is just draw in what the field would look like. A positive charge is going to be attracted to a negative charge. So we're going to see that attraction, but it diminishes as it goes out. And a positive charge is repelled by a positive charge. So we're going to see that repulsion, and it diminishes as it goes out. One of the things you'll notice here is my repulsion force is smaller than my attraction force was here because this charge was larger than this charge. So what that means for us is we're looking for a spot here that these forces would cancel out. Well, there's only one location that's true. It's here at position D. These forces cancel out. At position D, I'm attracted to this negative 7, the exact same amount that I'm repelled by this positive 2. And it feels weird. It's like, how could that be possible? Because I'm closer to the positive 2. But you're closer, this is also smaller. So that those two factors cancel each other to result in a situation where D could have an electric field strength of exactly 0. To know its exact position, we would need to know some more information about how far apart B and C are. But here, we can actually predict which of these would it be possible. All right, let's do some calculating here with more than one massive object that's attracting. Let's imagine here that you are on a space journey between the Earth and the Moon, and you're exactly halfway. I want to know what the field strength is there. So imagine this sheet that is being distorted by the Earth and the Moon. The Earth is going to distort that sheet more than the Moon. So halfway between, I expect my gravitational field strength is still going to be sloped towards the Earth, but the Moon is factoring in too now. So it's not going to be quite as sloped towards the Earth as it would have been without the Moon there. I want to figure out how each of these impact it to result in an overall field strength. And to do that, I'm going to take each of these separately. I can find little g based on just the Earth and little g based on just the Moon. To do that, I first need to know the distance that I'm going to use. I'm going to use half of this radius, half of the orbital radius of the moon. So instead of 3.8, I'm going to use 1.9 times 10 to the eighth because this is that distance from the Earth. It's also that distance from the moon. So that will be the most useful value for me. Then if I want to calculate the gravitational field strength of the Earth, I'll use this big G value, 6.67 times 10 to the negative 11th, multiply that by the mass of the Earth, divided by the distance I am to the Earth, that's halfway, that orbital radius, squared. And I get a field strength of 0.011 newtons per kilogram. So I am way out there. Remember, my field strength on the surface of the planet was 9.81. So I am much, much smaller. That is diminished greatly with distance thanks to that squared function. I can do the exact same thing for the moon. The only thing that changes is for the moon, I'm going to be seeing a mass that's a lot smaller. So 7.3 times 10 to the 22nd. If I do that, I'm going to get a field strength that's 0.00013 newtons per kilogram, even smaller. That's going to be pointed towards the moon. Now, that means that at this location, I experience two different force fields that are operating. Just like we did with net force, we can summarize these into one field strength, knowing that these are in opposite directions. I'm not going to add them. Instead, I'm going to take their difference. So 0.011 minus 0.00013 will give me a total field strength of 0.0109 newtons per kilogram, and that is going to be towards the planet Earth. So just a little bit less than it would have been without the moon playing a role at all, but the moon kind of evens it out just a bit. So an interesting question that you might have is, well, where would the spot be that gravity would fully cancel out? That it would be attracted equally to the moon as it is to the Earth. We know we can expect that's going to be a lot closer to the moon than it is to the Earth. And we could calculate it. I'll warn you, this is going to be a long walk to get there. Where would the object experience a gravitational field strength of exactly 0 newtons per kilogram? It's going to be somewhere closer to the moon than it is to the Earth. So let's just identify some variables. Let's say RE is the distance between the Earth's center and this magic 0 point. And RM is going to be the distance between this magic 0 point and the moon's center. Um, that means that the gravitational field strength, big G, times the mass of the Earth divided by the distance to the Earth squared should equal the gravitational field strength factoring the moon's numbers, the mass of the moon divided by the distance to the moon squared. Now, one way that I can simplify this is first start by taking a square root of everything so I can kind of get that squared out of there. And then G is going to be in both of them so that I can cancel. So I can cancel out G, take the square root of everything, and I get this. The square root cancels out that, or simplifies out that squared function. So I got square root of ME divided by RE is equal to the square root of MM divided by RM. Now I can cross multiply, or before I do that cross multiplication, let's look at one thing here. I can describe this in terms of each other, just so I have only one unknown. And let's say that the mass, or the radius, or distance to the moon, rather, is just going to be the total distance subtracted by the distance to the Earth. That's just kind of a shortcut that I can use. And if I do that, I can plug in the mass of the Earth, the mass of the moon, and then instead of the radius, or the distance to the moon, I can just say it is going to be, hold on, that's totally wrong. It's going to be not that. Let me factor in a new thing and I'll come right back. All right, we are in a better place now. That has been changed, so it now reflects what it should be. The distance to the moon is 3.8 times 10 to the eighth minus the uh, distance to the Earth there. If I cross multiply that, I end up with a term that doesn't look super simple, but is simplified on taking the square root of this, multiplying it by this term. And then I can just combine some terms. And ultimately, I can solve for this distance, the distance away from the Earth. It has to be 3.42 times 10 to the eighth. So almost the whole distance all the way to the moon. But at that spot, if you can imagine a sheet that's being distorted by the Earth and the moon, if I placed a marble right at that location, it would be perfectly balanced. It wouldn't go either direction. It would be equally pulled in both directions. This is a pretty advanced situation. As I mentioned, it's a pretty long walk to get there. But it's kind of a nice challenge for you to see how all of these might interact in some complicated ways.